Can the Game Boy Advance run Super Mario 64? You may only know me from my N64 developing videos, but here is some early footage of Joshua Barretto's backport of Super Mario 64 to the Game Boy Advance. This right here is early footage, and while doing a good port sounds impossible at first, let's actually see what's possible. The Nintendo 64 has a 93.75 MHz CPU compared to the Game Boy Advance's 16.8 MHz CPU, making the Nintendo 64 almost 6 times as fast on raw CPU power. Despite that, there is a possible port, and we'll find out how today thanks to this video sponsor, Squarespace. With my optimizations, I've gotten Mario 64 to compute a frame with only 25% of the N64 CPU capabilities on twice as complicated scenes, meaning we would only need about 23 MHz to compute a frame. With a couple of shortcuts, 16 MHz may sound reasonable at first. However, that's only the CPU code. The CPU does not compute triangles, transformations, it doesn't render pixel, and it doesn't compute materials and many more things. The N64 has a secondary processing unit, the RCP, which is a triangle crunching powerhouse with hardware parts specifically dedicated to rendering triangles. Whereas the Game Boy Advance only has the pixel processing unit, which actually just isn't useful for 3D rendering. The Game Boy Advance also only has 288 kilobytes of RAM, while the Nintendo 64 has almost 16 times as much RAM at 4 megabytes. Well, actually, the N64 has 4.5 megabytes, but the last half a megabyte is hidden, is a little weird, and I have a whole video about the secret half a megabyte as well if you want to see that. Either way, this gives the Nintendo 64 at least a 10 times speed advantage over the Game Boy Advance in terms of triangle drawing. And now that you understand just how impossible this seems, the reveal. It exists, and it works really well too.
Yo, we're playing Mario on the Game Boy. Let's go. Oh my god, on the video you can't even really tell it's a Game Boy game.
That is awesome. But why can Mario 64 run on the Game Boy Advance? Now, of course, given the huge power disparity between these two consoles, some sacrifices had to be made and a lot of workarounds and new innovations had to be made. But let's see how well it runs, and if the whole game can be remade, or if there will be roadblocks. To answer any question about the frame rates and viability of this all, I've invited Joshua Barretto, the developer of the Game Boy Advance port, to talk about this with us today.
Thanks for inviting me on. It's been a lot of work, but I'm looking forward to sharing the most interesting bits with you all.
So, obviously the Game Boy Advance does not have the RCP, so the entire rendering must happen in software. That means triangle processing will be super expensive compared to the Nintendo 64, and you only have a 16 MHz on this machine. It is kind of like playing a video game on a computer without a graphics card installed. A lot goes into rendering a triangle, and to hit 30 FPS at the full 240 by 160 resolution with a 16 MHz processor, you would only get 14 cycles per pixel. So how do you make that work?
To project a texture from the surface of an object in the world to our screen, we first got to understand that there's nothing to say that the texture's pixels, we call them texels, line up with the pixels of the screen. Our texture can be rotated, scaled, or stretched. In fact, the easiest generalization is to say that for a texture in a 3D space using orthographic projection, the straight lines of the x and y axes in the texture, known as texture space, can correspond to potentially any two straight lines in screen space. And so we go through our polygon pixel by pixel, row by row. For each pixel, we calculate where this pixel's location in screen space would appear in texture space. Usually we do this with a matrix transformation, but unfortunately this is far too expensive. To texture map the entirety of the GBA screen at 60 frames per second, we get no more than about 7 CPU cycles per pixel. A single multiplication can be several cycles by itself, and so this just isn't going to cut it.
Well, you will need some matrix math, right? After all, you do need to figure out the screen space coordinates for each vertex of each triangle that you draw.
Yes. Unfortunately, we can't avoid matrices entirely. To take a triangle from world space to screen space, we need to perform a matrix transformation of each vertex in the triangle. Thankfully, the GBA has both multiply and multiply accumulate instructions that allow us to do this reasonably quickly. The GBA's CPU, the ARM7 TDMI, has a faster multiplier than CPUs that came before. That's what the M stands for.
That explains how you draw triangles. But how do you manage working with such a tiny RAM?
There unfortunately isn't isn't enough RAM to keep entire stages loaded at once, and so we've got to pull things like mesh and texture data out of the ROM in real time every frame. Thankfully, the CPU's cartridge-based ROM sits on the end of a relatively fast 16-bit bus, and so provided we're careful to set up our ROM data in a format that's ready for the CPU to start processing it immediately, this is barely slower than preloading the data into RAM.
So obviously the Game Boy Advance was not made for 3D games, and it is lacking important features such as perspective correction and much more, similar to how the PS1 lacked those features.
Here, the PS1's primary constraint was its GPU, which was only capable of drawing a fine textured polygons. This means that the relationship between texture space and screen space is linear, which is incompatible with perspective projection. I tried playing around with rasterizers that do perspective correction for every pixel, but all attempts were too slow. And so I borrowed inspiration from PS1 developers, who lessened the warping effects of a fine texture mapping by subdividing polygon edges that experience large amounts of warping into smaller ones, reducing the most obvious cases of warping.
So on the Nintendo 64, the Z buffer is used while drawing an image to store the pixel depth of triangles that are already drawn on screen. We can then compare the depth of any new to be drawn pixels to the current Z buffer depth and only draw pixels of triangles if they are closer to the screen. This lets you draw triangles without sorting them first. With so little RAM, that seems impossible on the Game Boy Advance.
Yes, a Z buffer is sadly not viable. Even if there was enough available RAM for one, the cost of interpolating Z, comparing it with the Z buffer and then writing to the Z buffer for every pixel drawn would be unmanageably high. A typical solution to this problem is called the painter's algorithm. When implementing the painter's algorithm, we draw everything in the scene back to front, starting from the furthest element in the scene. This works great, but unfortunately sorting, as you may know, can be very slow. The cost of sorting grows more than linearly with the number of elements in the scene, and so sorting several hundred triangles every frame is very costly. To solve this problem, we use another trick. Turns out we don't actually care about perfect sorting. Most elements in the scene do not overlap or are separated by a significant depth, and so we can simply place every element into one of several hundred linked lists called depth bins, where each bin corresponds to a certain range of Z values. From there, we just iterate through the bins and draw things in the order we find them. Much faster.
Another thing we get nearly for free on the Nintendo 64 is perspective projection. This is what finds the position of a triangle's vertices in screen space. On the Nintendo 64, it is all just the matrix multiplication for up to 16 vertices at once, and it requires division by the depth value as well.
On the GBA, it's not so easy. We have to transform every vertex one by one, and, worse yet, the GBA doesn't have the ability to do division at all. Division is usually done with very expensive software emulation, effectively long division with a loop. And so here again I use a workaround. Instead of dividing by Z, I said pre-compute a huge lookup table containing the reciprocals of the Z value, and then multiply the vertex coordinates by the reciprocal. It's not quite as precise, but it's good enough.
Yeah, a lookup table like that would be awful on the Nintendo 64. But fortunately on the Game Boy Advance, memory speed is faster than it is on the Nintendo 64, which means that speaking relative to the CPU speed, it is much faster. And there's more, UV mapping sounds like another really tricky part here.
This is the most optimized part of the whole code base. When you're writing code this close to the hardware, there's a trade-off between flexibility and performance. One such example of this is how I choose to only support 32 by 32 textures in the game. By accepting this limitation, it allows us to squash both the U and V components of the texture coordinate into just one hardware register, as well as quickly transforming back out of that form to calculate the texel address in memory using just 2 instructions. By the way, thanks to Origami Science Guy for their help discovering this technique. It's one of the big things that makes this whole project viable.
Also, lighting. The N64 can do lighting very fast by doing a little bit of vector math and applying the light coefficient to each vertex individually. Obviously, this won't be feasible on the Game Boy Advance.
Here's the trick. To avoid having to do lighting calculations and the rasterizers in a loop, the game instead just picks between 6 pre-computed texture variants that have different lighting levels baked in based on their orientation. Unfortunately, that means jamming extra data into the ROM, but it's a price that must be paid in the name of performance.
That's great! Now you have all the features you need to render a 3D scene. All of these 3D rendering techniques left the frame rate just barely playable. But that is just step 1. Just because you can render a level, it doesn't nearly mean you have a fully functional game. You still need game code, collision physics, actor rendering, music, animations, and so on. Given how much performance just rendering the level already cost, how could we possibly add Mario to a level without killing the entire performance? Well, let's stick to Mario being just this one triangle for a second and talk about his physics first.
The GBA has no floating point unit unlike the Nintendo 64, and you can't do division. This is a serious limitation for 3D physics and especially collision detection. To get around this, the physics code uses only integer maths known as fixed point.
Fixed point math kinda works in a way that you have a big number and pretend it is a small number by dividing it by a power of 2, 256 in this case, which is super fast because computers are amazing at dividing by powers of 2. On the Nintendo 64, no such trickery was required because floating point math handled all this automatically, saving a lot of instructions in the process.
The performance budget is very tight, and so a lot of care has been put into exactly how collision detection and resolution works. Checking every triangle in the stage would not be fast enough. Instead, we bake an acceleration grid into the ROM that allows us to quickly look up for any position which triangles are closest by checking the grid cell that an entity is currently located at. Each grid cell contains a list of triangles that intersect the cell, allowing us to quickly narrow the search down to just a handful of potential candidates. From there, things are a little more traditional. The largest challenge was avoiding divisions in the vector maths. It took a while, but the physics code now contains exactly no divisions at all, not even via software emulation.
Now, obviously, Mario 64's Mario model has 768 polygons. That seems like a lot to handle for the Game Boy.
Yep, that won't fly on the GBA. Instead, we built a custom cut-down model of Mario with only 135 triangles. I'm not sure it's the prettiest form that Mario's ever been in, but it's recognizably him, and so that's enough.
You'll have to render other enemies too. I think we can all agree that Mario 64's assets were very rough, to be honest. I have a lot of Twitter posts and even a whole video up about reworking some of these actors to run better on the Nintendo 64 and look a lot less blurry.
Dealing with Super Mario 64's original assets has been a real challenge. A lot of them are very wasteful with their polygon budget, or are not properly watertight, or have huge amounts of overdraw. All of those things are a huge problem when running on the GBA. There just isn't the budget for inefficient assets. We've had to fix, optimize and simplify many of the original assets to get the game running acceptably. Goombas are now down to 22 triangles.
That still seems very expensive for how little power you have. Any plans to optimize that in the future? I imagine most actors you see won't even be 20 pixels on the screen.
In the future, distant entities will make use of 2D billboards to be swapped out with their models when the camera gets closer. One great optimization we've been able to do with entity models is pre-sorting their polygons into lists according to their position along each cardinal axis in the model. When the game runs, we simply use the list corresponding to whichever axis most closely matches the camera direction. It's not perfect, but again, perfect is the enemy of good with this project. The priority is speed.
And with that, Mario and other actors exist and are moving around. But there's one more super expensive thing you would need to implement that actually is way more expensive on the CPU than everything we've talked about so far combined. Animations and matrices. The Nintendo 64 computes actor and animation bone positions using a lot of trigonometry and matrix math. In my optimized engine, this alone cost me more than half of my entire frame CPU time. This is clearly not a viable strategy. Plus, the Nintendo 64 CPU only needed to compute a model matrix, which would then be sent to the RCP to get multiplied by vertex positions. The GBA has no RCP. Doing actual animations seems entirely out of the question. This seems like an entirely unclimbable mountain to me.
Exactly right. Proper bone-driven animations are just not viable on the GBA. The maths involved is just too expensive. We get around this problem by avoiding bones entirely and just animating the individual vertices directly. To do this, we pre-compute the vertex position for each animation keyframe and then interpolate between them as the game runs using some very cheap maths. All in all, it works out to just 6 additions and 3 multiplications per vertex, which is many times cheaper than bone animation would have been.
Wow, it really does look convincing. Of course, on the N64, ROM space is a huge hurdle that even led to a bunch of games being impossible to port to this console. And a fun fact here is that integer multiplication on the Game Boy Advance can be faster than on the Nintendo 64, despite the Game Boy Advance overall being slower due to the Nintendo 64's awful memory speed and its slow integer multiplication. The Nintendo 64's integer multiplication are actually kind of awful, to the point where they are significantly slower than floating point multiplications.
Yes, unfortunately this doesn't doesn't come without problems. Most games don't use vertex interpolations because it's a lot harder to control and can result in bizarre intermediate shapes between keyframes. Squashed limbs, inverted heads, you name it. We have to be quite careful to avoid these cases, or at the very least hope that the resolution of the screen is too low to notice.
Well, it's not like you'd see minor issues like that on the Game Boy Advance 240 by 160 display anyway. Alright viewer, now look at this footage. Something is missing here. Sound effects and music. Music is an issue. In Mario 64, all the music is mixed, kind of like a MIDI audio on the CPU. It's more expensive than game physics in my game even, so this will absolutely not fit within the Game Boy Advance strict CPU budget.
For the time being, audio is just stored in the ROM as uncompressed 8-bit sampled audio. This isn't ideal, but it is extremely fast and ROM space isn't a massive concern, at least not yet. In time I'd like to implement a proper audio sequencing engine, but it's going to be difficult to do that while staying within the tight performance budget.
That makes a lot of sense. I use a similar strategy on my Nintendo 64 game, and it ended up bloating my ROM from 12 megabytes all the way to 60 megabytes.
Regular GBA cartridges have a maximum size of 32 megabytes. We're already sacrificing a lot of ROM space, what with lookup tables, pre-baked lighting and much more. As time goes on and more features get added, care will need to be taken to make sure it all fits. But that's a problem for future me, and I am not yet future me.
Joshua told me that there are a lot more tricks involved in making this happen, such as palette tricks for water or shadows, and sprite rendering optimizations for Mario 64's many billboards. But talking about every little trick would go far beyond the scope of this video, so you will have to watch Joshua's videos for that. So, does that mean Mario 64 on the Game Boy Advance is confirmed? Well, there are still some challenges to solve. For one, all actors need to still be implemented. And keep in mind the imposter actor idea, so I think this is very possible. And also, all of the levels need to be implemented. Of course, even with the engine fully implemented and us confirming that everything is possible to remake, remaking the whole game itself would require an immense amount of pain and suffering. But this is an insanely cool proof of concept, and if he actually finishes the whole game, that would be absolutely insane. So regardless of how it goes, we got a cool tech demo out of it. Of course, there's also the option to still improve some of the engine features, like the perspective correction or find further triangle rendering speedups. So I'm very excited to see where this project will go. Maybe one day in the future we'll get this game running at a cinematic 24 frames a second on a 2001 handheld device. There's also this entire GitHub document Joshua sent me with further ideas he had to improve stuff that you'd only understand if you were an absolute programming and or Game Boy Advance nerd, but it's looking promising, and I do believe we will get a decently playable version of Mario 64 on the Game Boy Advance at some point in the future.
Thanks so much for inviting me on.
Currently, his build runs Mario 64 between 12 and 25 frames a second and is very well playable. If Nintendo got away releasing Ocarina of Time in Europe running at 16.67 frames a second, I think we can let Josh get away with this. Super cool for a console that's roughly a tenth the size of the Nintendo 64. The code is entirely portable and can viably be ported to other, similarly weak machines. Maybe this will introduce the era of Mario 64 being ported to dozens of devices just like Doom got ported. I would absolutely love to see Mario 64 running on more weird and underpowered hardwares. Thank you for watching. Shoutouts to Squarespace for sponsoring this video. Squarespace has all the tools you need to build a website. They help you find the domain with one all-inclusive price, no hidden fees, and each domain comes with privacy and security tools. They also offer SEO tools to help your website pop up at the top of Google search. If you like to showcase videos on your website, Squarespace also has the tools for that. You can upload and organize your videos, and if that is what you're into, even monetize or paywall your videos. Go to squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/Kaze Emanuar to save 10% of your first purchase of a website or domain. If you would like to see more optimizations, check out all the stuff I've been doing with Mario 64. We're trying to get a similarly optimized game going, except we're doing it on the Nintendo 64 instead of the Game Boy Advance. Shoutouts to all my Patreons for supporting me on my journey. In the background you can see footage of the game that I was just talking about. This runs at least 30 FPS stable on Nintendo 64, with a lot of areas even hitting 60 FPS if you enable 60 FPS in your options. I will look forward to this game, I am working very hard on it.